In this demonstration, we're going to look at the RxFusion Lab software. RxFusion Lab is an interactive C++ programming environment for developing sensor-based IoT applications that might execute in an edge device. It's built on the RxFusion C++ framework, which implements the reactive programming paradigm, which is an increasingly popular programming model which fits very well with edge device programming. Actually, it's not too bad for programming gateways or data center devices as well, servers as well. But here we're just looking at applications for edge devices. So on the screen you see a couple pictures. On the left is the Lattice iStick. This is a small, inexpensive development board from Lattice. It has a Lattice FPGA on it, a programmable device, and a PMOD connector on the end. And you see it's a USB device. I currently have one of these plugged into my laptop with a USB extender cable, so it's free to move about. On the right side, you see a picture of the Diligent accelerometer. This is a 3-axis accelerometer from Diligent, which has also a PMOD connector on it. So I currently have one of those plugged into the connection on my Lattice iStick so that I can use the accelerometer in this live interactive environment to develop with some actual sensor data and explore the design space a little bit. Okay, so let's take a look at how this actually works. Down below I have 3 cells with some C++ code that I've already entered to get started, and I can execute these live in the background. So I just executed that first box, which included the RxFusion Lab header file. In the second box, I'm just creating a typedef to rename the tuple 3 int to XYZ. Because we're working with the accelerometer data, it's 3-axis, so we're going to get tuples with 3 values, one for each axis, as samples from the device. It's just tedious to type the tuple 3 int all the time. Okay, now I'm going to instantiate the Diligent ACL object, which is part of the framework, and just instructs the framework that that's what I currently have attached to the iStick, and it provides the interface for me to collect data from it. And you can see also part of that is specifying that it's sitting on COM port 9. Below that, I've declared a trace object, which is a generic collection object which holds trace data. And so in this case, I'm holding trace data, tuple trace data. Okay, so now what we want to do is actually capture some data from this device live. So I'm going to call the capture method. I'm going to ask for 50 samples from the device, and I'm going to instruct it to store that data in the trace object. So the capture is actually running right now, and I'm literally moving the iStick up and down so that we get some interesting waveform data. So let's just plot the data that I collected. And I can plot that right here in my window. And so you can see these kind of nice up and down movements that I was making with the device. Now let's take a look at our first RxFusion operator. So reactive programming. In reactive programming, you have observables, which are basically streams. And you have stream operators, which transform those streams in a functional way. In C++, we use the greater than operator, which in C++ they call the extraction operator. But I generally read it pipe to when I'm doing RxFusion work. So I'm going to take this trace data that I have in the raw object, and I'm going to pipe it to the built-in average operator. It's a template operator. I have to tell it what kind of data I'm averaging. In this case, I'm averaging these tuples. And I also specify this is a rolling average. I have to specify the number of samples that I'm averaging over. So let's do a 4-sample rolling average. And then I can just re-enter this to update my plot. And here's the same data, but I've smoothed it out a little bit with the average operator. Okay, so that's nice. We were able to capture some data and make a nice plot of it. Let's see how we would actually develop an application now. Let's say we were trying to build a pedometer and we wanted to be able to count these peaks in order to count steps. What we're going to do is let's just pick out one of these waveforms out of the 3 and just work on that one and try to count these steps. So I'm going to create another trace object to hold some data. And let's take my original data and pipe that through the projection operator. So project 2 is going to give us the waveform 2 here out of our trace, this one here. And it's projecting from a tuple to an integer because we're taking out a single integer. And then let's pipe that to our average operator. Now we're working with ints because we've extracted that one int out. And again, we'll average it over 4 samples. And let's take the result of all that and put it in my new temporary trace object. Let's just take a look at that. Oops. So we can see what we're dealing with. So there it is. That's that third axis extracted out and then run through the average operator. Okay, so my general strategy here for counting steps is going to try to detect the rising and falling edges of the waveform. And the way I'm going to do that is I'm going to take the original sample value and I'm going to compare that to the minimum and maximum values over the last 8 samples. So I'm going to have a rolling minimum and a rolling maximum. So I need all 3 of these values to work with. So I'm going to transform this data from integers back into a tuple of 3 integers, the current value, the rolling minimum, and the rolling maximum. So let me just create a trace to hold that. And now we'll construct this tuple. So the first element of the tuple is going to be the original values. So that's just the smooth trace that you see up above. Now the AND operator is how I combine multiple streams into a tuple. So I'm going to take a second stream, which is going to be the same smooth data, but this time I'm going to pipe it through the built-in min operator over a window of 8 samples. And then I'm combining that with a third stream, which is the original data piped through the max operator. Okay, so I have 3 streams here, the original and 2 transform streams, one that's computing the min, one that's computing the max, and the ampersand is joining those together into a single stream of tuples. So let's just pipe that result into my trace variable so we can look at it. So here you can see we now have three streams: the original stream in red, the max in aqua, and the min in blue. So far we've been using just the built-in operators that come with RxFusion. However, the power of the framework is to be able to build your own operators and transform your data in your own application-specific ways. And the reactive programming model allows us to do that through a number of functional programming operators that we can apply to streams. So we're now going to use one of those, which is called map. And the map operator allows you to specify a custom function which is applied to every incoming input value and produce any arbitrary output value. So in this case, I'm going to create a map operator which is going to take this tuple, the stream of tuples that I just produced, the XYZ, and I'm going to compute some output as an integer. So it's a map from XYZ to int. And the argument to the map operator is actually a function, the function that I want to apply. We're going to use the C++ 2011 standard syntax for specifying an anonymous function. If you're not familiar with anonymous functions, it's just a way of specifying a function inline right inside an expression without having to declare it separately. It's very convenient and elegant for streams programming. So instead of declaring a function foo that does something and passing it in as a pointer, I'm actually going to pass in the function right directly here in my map argument. So the syntax here, as you see, the square brackets is the beginning of an anonymous function. In parentheses, we have the arguments, so I'm taking in a vector of XYZ, which is the data type that is coming through my stream. And the arrow int is indicating that I'm going to return an integer value. And then in curly braces, I'm actually going to provide the body of my function. So first, let's detect positive edges. I'm going to take the first element of the tuple, which is coming from this first stream here, smooth. So this is the original value. And I'm going to subtract from it the second element of the tuple, which is the min value that I computed. So I'm subtracting the current value of my stream with the rolling min over the last 8 samples. So this is going to basically give us the delta of how much the signal has changed over the last 8 samples. And if it's greater than 30, I'm going to call that a positive edge. Now I'm going to do the same for the negative. I'm going to take the maximum value, which is in element 3 of our tuple, subtract off the current value, and if that's greater than 30, I'm going to call that a negative edge. So either of these will be 1 or they'll both be 0, but they're never both 1. So if I return pos minus neg, either it's a positive edge, I'm going to return 1, it's no edge, they're both 0, I'm going to return 0, or it's a negative edge, pos is 0 and negative is 1, so I'm going to return negative 1. So let's take the results of all this and put it into a temporary variable, which I don't have one. So let me just quickly add one here. Okay, so this is producing integers, so I need an int trace here now. These are going to be edges. Okay, so now going back to this, I can type this into my edges trace, and now let's take a look at what that looks like. Okay, so now I've detected the edges from my waveform. So basically I have 3 peaks and 3 valleys. The nice thing about this approach is I have very simple parameters that I'm using to detect edges. The width of my edges have to be at the most 8 samples because that's what I'm using for my min and max windows. And the edge also has to have a magnitude of at least 30. And so with these 2 simple parameters, I can easily configure what kind of edges are acceptable in terms of the width and the amount of arise that I expect. Okay, so let's finish this out and get something where we can actually count these steps. So first of all, I have a bunch of zeros in here. I want to get rid of those because I want to count how many times I'm alternating back and forth between a positive edge and a negative edge. So to do that, I can apply another functional operator filter. This one takes a function, returns a boolean to indicate whether we want to keep the value or not. So we're going to filter out values here. So again, I have an anonymous function. It takes now we have integers. It takes int as an input, and I only want to keep the non-zero values. Let's actually just put this in a plot so we can see what that does. Okay, so I've just filtered out the 0 values from this plot, and so now I have just my pos edge, my negative edge. So I'm just going back between positive 1 and negative 1, and you can see here how I can easily count steps. One last thing here is I have multiple outputs for each edge, and I actually want to get rid of those, and I just want actually one. So I can just pipe that to the distinct built-in operator, which only outputs unique objects. So if there's any repeats, if I get 1, 1, 1, it's only going to output 1 value for those. So now I get basically, so now this is basically what we wanted. We have a stream that's outputting 3 ones for our 3 peaks and 3 negative ones for our 3 valleys, and we can easily count those up and keep track of how many steps the user is taking. So we're not going to go any further with this, but this data you could keep a counter, aggregate that, and send it upstream through the network. So this has been a first look at the RxFusion Lab. I find it really a great tool just to do this kind of interactive design and prototyping, which can be easily incorporated into an application when you're done. There are actually some file operations where you can actually export this code so that you can put it into an actual application. And future videos we'll look at some more advanced operators, and also how this applies to not just edge devices, but other devices in the IoT ecosystem. Thanks for watching.